Hi, I'm Yu. Today I will talk about sublinear algorithms and lower bounds for matrix TSP cost estimation. This is a joint work with Sampath, Kannan, and Sanjeev Khanna. Let's first review what is matrix TSP. Given a weighted complete graph, a traveling salesman tower is a cycle that visits each vertex once. And then the traveling salesman problem, which is short for TSP, is the problem of finding such a tower with the minimum cost. While in matrix TSP, the distance between vertices is a matrix, which means it is symmetric, and more importantly, it satisfies the triangle inequality. Matrix TSP can be approximated within a factor of 1.5 in polynomial time by the famous Christophidis algorithm, which includes finding a minimum spanning tree and then find a maximum matching among the odd degree vertices. Surprisingly, it is still state of the art despite it is being around more than 40 years. But on the other hand, matrix TSP is also APX hard, approximating matrix TSP within a factor of 123 over 122 is NP hard. While we still don't know if we can break the 1.5 barrier for the general case. For some special cases, we have some positive results. One case is the Graphic TSP. In Graphic TSP, the distances between vertices corresponds to the shortest path distance in a connected unweighted graph. Another special case is 1-2 TSP. In 1-2 TSP, the distances between vertices are either 1 or 2. In polynomial time, Graphic TSP can be approximated to a factor of 1.4, and 1-2 TSP can be approximated to a factor of 8/7. It is worth noting that 1-2 TSP can be reduced to Graphic TSP in an approximation-preserving manner. Given a 1-2 TSP instance, consider the unweighted graph made by all weighted 1 edges. And then, we add a new vertex and connect it to all other vertices. Consider the Graphic TSP instance generated from this unweighted graph. The distance between any two vertices is 1 or 2, and it is also equals the distance between them in the original 1-2 TSP instance. In this work, we consider the query model. In this model, the algorithm is allowed to query the distance between a pair of vertices, and the question is, how many queries do we need to solve matrix TSP? Compared to the classic model, on one hand, we do not know the whole graph if we only made a small number of queries. While on the other hand, we will have unbounded computation time, so the NP-hard results didn't apply here. In query model, minimum spanning tree can be approximated within a factor of 1 plus epsilon with near linear number of queries. So matrix TSP can also be approximated within a factor of 2 plus epsilon with this number of queries. Remember that given a spanning tree, we will have a TSP tower whose size is twice as the size of the spanning tree because of the triangle inequality. So the question is, can we do better than 2? And can we even push to 1 plus epsilon? In this work, we prove several results on both positive and negative side. On positive side, for Graphic TSP problem, we give an algorithm that approximates Graphic TSP within a factor of 2 minus epsilon with near linear number of queries. And for 1-2 TSP problem, we give an algorithm that approximates the TSP size to within a factor of 1.625 with near root n queries. On the negative side, we prove that any algorithm that approximates 1-2 TSP within a factor of 1 plus epsilon needs nearly n square queries, which means we need to query almost the whole graph. And this lower bound naturally generalized to Graphic TSP and matrix TSP. In this talk, I will focus on the first result, which is an upper bound for Graphic TSP. Before going further, let's first make the concept of approximation factor clear. In Graphic TSP, the size of TSP is at most 2n because the underlying graph is always connected, which means there is a spanning tree of size n. We require the output always larger than the real answer. Otherwise, square root of 2 factor is trivial, because the TSP size is always between n to n, so we can just output square root of 2n. Note that to get a 2 minus epsilon approximation, we only need to recognize the case when the graphic TSP is either very small, which means it is smaller than 1 plus epsilon n, or very large, in which case it is larger than 2 minus epsilon times n. The concept of biconnected graph is very important in our algorithm. A connected graph is biconnected if it remains connected after removing any vertex. Let's look at some examples. The graph on the left is biconnected, since removing any vertex the graph is still connected. While the graph in the middle is not biconnected. Removing the middle vertex will break the graph into two pieces. And the graph on the right is biconnected, since a single vertex is a connected graph. Note that this graph has minimum cut size only 1, so a biconnected graph may be not two edge connected. Given a graph, a block is a maximal biconnected subgraph. Any graph can be decomposed into blocks, and if a block only have two vertices, we call this block a bridge. We note that any two blocks share at most one vertex, because otherwise, the union of them is a bigger biconnected subgraph. If two blocks do share a single vertex, we call this vertex an articulation point. We call the result of block decomposition a block tree. Let's look at an example. In this picture, each yellow area is a block, and each red point is an articulation point. It is easy to see that the sum of block sizes equals the number of vertices plus the number of blocks minus 1, as the original graph can be built by the blocks one by one, and each time we add a new block, exactly one vertex in the new block is already in the graph. Also, the cost of graphic TSP of the original graph is the sum of graphic TSP of all blocks, since the union of the TSP tower of all blocks is the TSP tower of the original graph. By these two observations, we have a lower bound on the cost of the graphic TSP of the original graph, which is the number of vertices plus the number of blocks minus 1. So if a graph has many blocks, the size of the graphic TSP is very large. While the blocks might be hard to detect in the query model, we focus on some special vertices we call bad vertices. A vertex is bad if it has degree 1 or it is a degree 2 articulation point. If a graph has too many bad vertices, the cost of graphic TSP is large. In fact, around each bad vertex, there is one or two bridges. The size of the maximum matching in the underlying graph also plays an important role in our algorithm. We claim that if the size of maximum matching is small, then the cost of graphic TSP is large. To see that, consider any TSP tower. We divide the tower into even steps and odd steps. Both even and odd steps cannot contain edges in the underlying graph more than the maximum matching size. Now we describe the algorithm. We approximate the size of maximum matching and also the number of bad vertices. If the maximum matching size is small, or the number of bad vertices is large, then we already know that the graphic TSP size is non-trivially larger than n. But actually, if both conditions are false, the cost of graphic TSP is non-trivially smaller than 2n. Now we prove this statement, which means we need to focus on proving the upper bound of graphic TSP. Suppose a graph has ni vertices. The size of a graphic TSP of this block is at most 2ni minus 2 because the spanning tree has size ni minus 1. Now, suppose some blocks has the size of graphic TSP smaller than that. Specifically, suppose block I has graphic TSP cost 2ni minus 2 minus ki. The cost of the graphic TSP of the whole graph is the summation of 2ni minus 2 minus ki, which is equals to 2 times summation of ni minus 1 minus summation of ki. Now, because the sum of block size is equals to the number of vertices plus the number of blocks minus 1, we have the size of graphic TSP is equals to 2n minus 2 minus summation of ki, which means if there are many ki which is larger than 0, or if there are some ki's which is very large, then the size of graphic TSP of the whole graph is small, which means we need to focus on the graphic TSP on each block. The following lemma is a corollary of some previous results about graphic TSP. The proof involves some technical detail, so I will omit it due to the time limit. It says, if a biconnected graph has at least 3 vertices and also have a maximum matching of size m, then the cost of graphic TSP is at most 2n minus 2 minus 2n over 3. This lemma tells us that if a biconnected graph contains a large matching, then the cost of graphic TSP is small. With this lemma, we immediately have the following properties. If a graph has a matching with m prime edges which is not a bridge, then we know that the cost of graphic TSP is at most 2n minus 2 minus 2n prime 3, because remember that the cost of graphic TSP of a graph is the cost of graphic TSP of all its blocks. Also, any block with at least 3 vertices will have TSP cost at most 2mi minus 3 because the matching size is at least 1. So for all of these blocks, we will save 1 at least for the graphic TSP. So if a graph contains many blocks of size at least 3, then its graphic TSP size will be distinctly less than 2n. Now we are ready to prove the upper bound. Remember, our goal is to prove that suppose a graph has almost no bad vertices and also has a matching size which is not too small. We want to prove the cost of graphic TSP is small. By small, we mean it's far from 2n. We consider two cases. The first case is the number of bridges b is small, which is smaller than m over 2. This case is relatively easy because now we know that the number of non-bridge matching edges, m prime, now is larger than m over 2. So by the lemma, we have the graphic TSP cost is smaller than 2n minus 2 minus 2n prime over 3, which is 2n minus omega n. The other case is when the graph contains many bridges. In this case, we consider its block tree. Now consider the leaf blocks. If the block is a bridge, then it will contain a degree 1 vertex, which is bad. Otherwise, it's a non-bridge block. Now consider a vertex in a bridge. If it is not an articulation point, then it has degree only 1, which means it's a bad vertex. If it is an articulation point and only connects to one other block, if this block is a bridge, then the vertex is a degree 2 articulation point, which will also mean it is a bad vertex. Otherwise, the other block is a non-bridge block. If it is an articulation point participates in at least 3 blocks, then it has degree at least 3 in the block tree, which means there are more leaves in the tree because the average degree of the tree is less than 2. So any vertex of degree 3 will create more leaves, which contains a bad vertex or it's a non-bridge block. To sum up, any vertex in a bridge is either a bad vertex or it will create non-bridge blocks. So the number of non-bridge blocks is at least the number of bridges minus the number of bad vertices. So in this case, graphic TSP cost is at most 2n minus 2 minus the number of non-bridge blocks, which is 2n minus omega n. So in both cases, we have proved that the graphic TSP is distinctly smaller than 2n. So we have proved the correctness of our algorithm. The only missing part is how to implement the algorithm, which includes how do we approximate the size of maximum matching size and how do we approximate the number of bad vertices in query model. We first log bad vertices. We claim that we can determine if a vertex v is bad in order n queries. We first check the degree of v by querying the distance between v and all other vertices. If the degree of v is 1, then we can output v is a bad vertex. If the degree of v is at least 3, we can output v is not a bad vertex. Now, if the degree of v is 2, suppose the two neighbors of v are u and w, then we check if there is a vertex x such that the difference between the distance of u and x and the distance of W and X is smaller or equal to 1. If V is an articulation point, then we can partition the graph into two pieces like the left picture. The shortest path of any vertex on the left to W must include vertex U and V, and the shortest path of any vertex on the right to U must include vertex V and W. So in this case, for any vertex except V, the difference between distances to U and W is at least 2. If V is not an articulation point, then V is included in some circle because U and W are still connected after deleting V. Now consider the minimum cycle which contains these three vertices, and the vertex X with the maximum distance to V on the cycle. If it is an odd cycle, then the difference of the distances from X to U and the W is 1. And if it is an even cycle, X has the same distance to V and W. So vertex V is bad if and only if such a vertex X does not exist. To approximate the number of bad vertices, we can sample near linear number of vertices and test if each is bad. The approximation factor is guaranteed by Chen bound, and total number of queries is near linear. Then we consider the matching size. In query model, in fact, the approximation of maximum matching size itself is an important problem, and there is a lot of work about it. A work recently gives an algorithm that approximates the matching size within a constant factor by near linear number of queries. Thus, we can implement the algorithm in near linear number of queries. And this finished the proof of theorem 1. Notice that the algorithm heavily relies on estimating the size of the maximum matching. In fact, since until now there is no algorithm that approximates the size of maximum matching size within a small enough constant factor in query model, the approximation rate of the Graphic TSP of our algorithm is also just slightly smaller than 2. So, a natural question is, can we avoid estimating the matching size, or is it necessary? The answer is it is necessary. In the remaining of the talk, I will talk about a reduction from matching to 1-to TSP. Naturally, it is also work for Graphic TSP and the general metric TSP. We prove that any algorithm that estimates 1-to TSP cost to within a 1 plus epsilon factor can be used to estimate the size of the largest matching in a bipartite graph on 2n vertices within an additive error of 5 epsilon n. Notice that this reduction works for most of commonly used models, not only query model. Given a bipartite matching instance with 2n vertices, we create an 1-to TSP instance with 4n vertices. The picture only shows the weight 1 edges. All other edges have weight 2. The vertices are partitioned into 5 sets, where V1, V2, V3 have n vertices, and V0 and V4 have n over 2 vertices. The edges between V1 and V2 is just the original bipartite matching problem. The edges between V0 and V1 is a perfect 2 matching. The edges between V2 and V3 is a perfect matching. And the edges between V3 and V4 is a complete bipartite graph. If the original bipartite graph has a perfect matching, then the 1-to TSP instance we created contains a TSP tau of size 4n. In the picture, we rearrange the vertices in V3 and V4 so that the ith vertex in V1 is matched to the ith vertex in V2. The TSP tower we show in the picture has size 4n. In fact, by a careful case analysis, we can prove that even if the original bipartite graph does not have a perfect matching, the TSP tower we show in the picture is still optimal. So, the TSP cost is 5n minus the size of matching in the original bipartite graph. Which means, if we have a 1 plus epsilon factor approximation of the 1-to TSP cost, it is at most 5 epsilon n additive error, and so we will have a 5 epsilon n additive error approximation of the original bipartite matching problem, which concludes the reduction. Thanks for listening. If you have any question, please ask me in the discuss session or just send me an email. Thanks.